We hope PPT is visible now. Yes or no? PPT. Yes or no? PPT is visible. I hope it is visible. If any issues, please tell me. I want to answer yes or no. Is it PPT is visible now? Pawan.
Yes, sir.
Yes, sir. Yes, sir.
Just I'll give a brief introduction. 5 minutes. I'll finish that derivation once again. Important steps only I will explain. Then we'll go for problems. Today I planned for the problem only. So you are starting from this equation, Galerkin equation, and we have phi. So function phi is nothing but a temperature function. When it comes to heat transfer, in the derivation, inside the derivation, there is a term phi. So phi refer to temperature function or nodal temperature function or nodal temperature vector. The later stage, you are writing the expression for phi in terms of n into xi. So phi refer to temperature at any point within the element. That temperature we can get it by knowing the shape function n1 and n2 as well as the nodal temperature xi1 and xi2. So those xi1 and xi2 are virtual temperature. So when you come to your derivation, you have to remember T1 and T2 are referred to nodal temperature. Those are the actual temperature. But approximate temperature or virtual temperatures are referred by xi1 and xi2, or this xi in our derivation you are writing as n into xi. So where n is n1, n2, it is a row vector, and xi is xi1, xi2, xi3, etc. Those are the virtual global vector, and we have this term, the differentiation equation -1. This is nothing but heat transfer equation or governing differential equation for conduction. If it is for the combined conduction combined with convection, we have governing differential equation conduction combined with convection. If you are dealing with the derivation of fins, so then this term is nothing but, so we have to derive one more set of equation for the fins. So I think why students are you can join through your mail. So don't use the link every time. I have to click. I have to admit here. I am repeatedly telling. Still you are doing it. Will interrupt the classes. So in simple way, phi is temperature vector. So d of t minus q refer to the different governing differential equation. Now, so equation 1 is for the governing differential. Is it PPT is visible now? Yes or no? PPT. So please.
Yes, sir.
Okay, okay. Then equation 1, the referred to, because another two derivations are there, 2 or 3. But equation 1 is for combined conduction. The second term is for the conduction term, and third term is for convective term. But we are deriving the equation only for the conduction. Hence, you are neglecting the third term. So you are considering only the first two terms. First two terms are correspond to only conduction. Then your RD equations, the residual is nothing but k into d square t divided by dx square plus q. It will be the residue. Then you have to substitute the residue. Same thing is given here. Once you substitute and multiply, so if you expand the term, you'll get term 1 and term 2. So equation number 5 consists of term 1 and term 2. The term 2 is mainly for the heat generation vector. The term 2 is, we are getting from the term 2, you are getting the equation for the heat generation vector, that is nothing but RQ. The lower letter RQ for elemental heat generation vector. The capital letter RQ is for RQ, sometimes it is about the R infinity, that is for the global heat generation vector. And first term, if you differentiate this, integrate, if you go after a differentiation and integration, we get two equations. So one term is correspond to the thermal conductivity vector, or first term, from the first term after simplification you get thermal conductivity vector, and the second term, so we'll get the RQ or heat generation vector. So now we are considering the first term by integration by parts. So you are simplifying it further. So then for applying the limit, etc. One function you have to remember, we have a temperature function phi of 0 is equal to 0, or function phi is equal to 0 where temperature is specified. So then it function phi is 0. Now you have the first term, you are simplifying the first term that I am already you have discussed. And only one point, this equation you have to remember. Imagine we have the heat, you are heating the steel rod from the one end, and through the steel rod, heat is conducted through conduction. Now, if you come to the right end, outermost other end of the steel rod, one rod you are heating, other end is exposed to the atmosphere. Throughout the steel rod, the heat is conducted, but when you come to the tip of the steel rod, whatever the heat conducted, it is the same heat goes to atmosphere through convection, or we can say that at the end of the steel rod or heated rod or hot rod, so whatever the amount of heat conducted, that is transferred to the surrounding medium by convection. Hence, you are equating the conduction. How much amount of heat conducted is equating to amount of heat convected. That is applies only at the tip of the rod. So then you have to go for simplification, for simplifying the terms further. But you have to remember here, this you are using the function phi. So phi refer to temperature function or temperature at any point within the element. Suppose temperature at node 1 is xi1. So temperature at node 1 is xi1. Temperature at node 2 is xi2. Temperature at any point within the element we can get it from xi is equal to nq. So now xi of L is equal to n of L into xi of L. So n of L, or it is nothing but a shape function at x is equal to L, it is given by 1 into xi of L, or you can write the phi of L is also equal to xi of L. This equation you are repeatedly using. Your U is equal to NQ. When come to beams, so U is replaced by V. The displacement at any point within the beam element is given by HQ. But for the bar, so same equation can be written as U is equal to NQ. When come to temperature problems, so where you can write T is equal to N of element into T of element. T of element is nothing but the nodal temperature, T1 and T2. Now we have the second term. Within the first term, we have second 1B term. You have to simplify it further. But you have to remember, I think yesterday one student is asked, that's a good question. So initially we were started with the global coordinate. From global coordinate, you are slowly moving to natural coordinate. Hence, your integration limit changes from 0 to L, 0 to L to -1 to +1. We have global X, its value ranging from 0 to L. But when you come to xi coordinate, it is a natural coordinate. Sometimes natural coordinate is also referred as local coordinates, where xi value ranging from -1 to +1. So x is the dimension. The dimension of beam may be length ranging from 1 meter to 10 meter, 100 meter, whatever it may be. But once we define the element in terms of natural coordinate, so one end of the beam, the xi value is -1, and at the another end of the beam, the xi value is +1. So now this type of question may comes for your objective questions if it is next online test. So what is the value of xi at node 1? What is the value of xi at node 2? Value of xi at node 1 is -1. Value of xi at node 2 is +1. Exactly at the midpoint of the element, the xi value is equal to 0. Those type of question, if next test is objective type or multiple choice question, so such type of question may comes. Now everything, initially we have started from global coordinate. So you are moving from global coordinate to the natural coordinate. When you moving from global to natural coordinate, every term consists of x is replaced by xi. So those modification you are doing. We have xi equation, you are differentiating, and finally you are getting, you have to replace dx in terms of xi. And we have general formula, it is nothing but interpolation function. So once you know the temperature at node 1, that will be T1, and once you know the temperature at node 2, it will be T2. So we can get the temperature within the element at any point within the element, or any substitute any value for the xi. So xi ranging from -1 to +1. So we will get the temperature at any point within the element. We have kT is equal to Q. That is the global thermal equilibrium equation. By using kT is equal to Q, already we have solved one problem. We are getting the temperature T1, T2, T3, etc. Those temperature is only at the nodal point. If you want to know the temperature other than the nodal point at any point within the element, so instead of going for fine tuning the mesh, or going from finer coarse mesh to the finer mesh, so without doing any finite element process, by just using interpolation function, so without using your complete finite element concept, by using interpolation function, we can get the temperature at any point within the element by using the shape function or interpolation function n1 and n2. Already we have defined n1 and n2 for heat transfer element. Same equation holds good for the bar element. The bar also n1 is equal to 1 minus xi divided by 2. For beam n1 is different. N1 is replaced by h1, h2, h3, h4. The shape functions are 4 for the beam. For the thermal element, there are 2 shape functions, n1 and n2. If it is objective type questions, you may get questions like this. How many shape function for linear thermal element or heat element? You have to say the 2. Answer may be given like 1, 2, 3, 4. The correct answer is 2. There are 2 shape functions, n1 and n2, because you are going for the linear thermal element. Then you have to go for differentiation, all those things. Finally, you will get dt by dxi. So finally, we have dt by dx. dt by dx is nothing equivalent to strain in your regular structural analysis. But dt by dx refers to the rate of change of temperature along the x direction. Suppose you are heating the rod at one end, let it be one end temperature is 1000 degrees Celsius. Extreme other side temperature may be 100 degrees Celsius. How temperature changes from 1000 degree to 100 degrees Celsius, that is given by equation dt by dx. That is nothing but the how temperature changes along the x direction. That again you are getting equation, that is nothing but bt matrix, that also we have derived in the previous class. Now here we have slight different concept. So now imagine, instead of saying temperature T1 and T2, so we are saying that temperature is given by xi1 and xi2, xi3 up to xi. Those are referred to virtual temperature, global virtual temperature. So now we have using the function phi. The phi we are writing in terms of n into xi. So where for the thermal element or heat element, n is given by n1 and n2. Just you have seen n1 and n2 here. For thermal element, the shape functions are n1 and n2. That you have to remember. N1 value is 1 minus xi divided by 2. N2 value is 1 plus xi divided by 2. By using that, so now we can writing phi is equal to n into xi. So that also we can write it as like this. Xi of t is equal to n into xi transpose. That's also equal to n transpose into xi transpose. That you are taking out the term separately. You are taking the separately for transpose for n. In the similar way, you are taking the transpose for xi also. Then we can write xi is equal to n xi. So this also can be written in the other way also. Xi transpose into n transpose also you can write xi is equal to. There is a mathematical derivation. But in time being, as per your heat transfer is considered, so we can write phi. Phi is nothing but temperature at any point within the element or temperature function at any point within the element is given by xi transpose into n transpose. This complete xi is replaced by xi transpose and n transpose. This is phi and this is xi. And finally, phi of L is equal to n of L into xi of L. The n of L is equal to 1. At x is equal to L, n of L is equal to 1. And finally, we'll get xi of L. So now this is the second term. This is the first term only. So now if you simplify it further, so we have two functions dt by dx and one more function is dxi by dx. So we know that dt by dx is equal to b transpose into te. This is a temperature function. And dxi by dx is again one more temperature function. Hence, we can write it as, instead of going for one more derivation, so it is nothing but equivalent to strain. This is B transpose matrix, B matrix into xi. Instead of T, it is replaced by xi. That also you can write it as xi transpose into BT transpose. That equation already you have written. So finally, say first term, we are ending with equation for K matrix, and the second term, this is the second term in the equation number 5, that we are ending with R matrix. So that means after simplification, etc. So finally, we will get see here. This is equation number 5. This is the first term. After simplification, first term will get first. This is correspond to your K matrix. This is correspond to R matrix. This is correspond to R. This is K matrix because we have the integral sign. So inside the integral sign, we have elemental matrix. But once you take the integration, you get the final K matrix. K transpose KT. T is for the temperature or thermal conductivity. We can take it as a thermal conductivity. Just to differentiate between the stiffness matrix K and thermal conductivity matrix, we are putting subscript that T is for the thermal conductivity matrix. So R is nothing but your force vector. In we have studied about KQ is equal to F. So KQ, so this is K is replaced by K transpose, K, not transpose, KT, and Q is replaced by temperature vector is equal to, because xi of t and xi and will get cancelled. So this will get R. R is nothing but a force vector. We have the equation for K of t, and if we simplify, after multiplication and simplification, we'll get the thermal conductivity matrix. Thermal conductivity matrix given by K T is equal to Ke divided by Le, so and so. But in some cases, it is multiplied by A. In suppose in the question, the area is given. The area normal to heat transfer rate is given. In such, only on such cases, you have to multiply by AE. Strictly speaking, you can write it as KT is equal to AK divided by LE. It is almost similar to AE divided by LE, where in the case of structural problems, so E is the Young's modulus. When you come to thermal problems, the Young's modulus is A remains same. A is area, the area normal to the direction of heat flow, and E is replaced by the thermal conductivity divided by L. The L refer to length of the element. It is almost similar to the stiffness matrix for the bar element. In the similar way, we'll get one more vector, R vector. So R vector is nothing but RQ. So we are using capital letter R and lowercase letter r. Once you write capital letter R, that is the global heat rate generation vector. Capital letter R is nothing but global heat generation vector, because we have summation of I is equal to 1 to n. So we have the, imagine there are 10 elements. So we'll get R1, R2, R3 up to Rn will get, like what we have done for the stiffness matrix. If there are 3 elements, the global stiffness matrix K is equal to like K1, K2, K3, etc. In the similar way, capital letter R refer to global heat generation vector, and lowercase letter r refer to the element heat generation vector. We know the n1 and n2 value for the heat transfer element. N1 is equal to 1 minus xi, n2 is equal to 1 plus xi divided by 2. If you substitute and after application, the integration limit, etc., the finally end with your RQ, sometimes it is referred to capital letter Q, that's equal to QE LE divided by 2. QE refer to heat generation vector. And in the same example, if you have iron box, within the iron box there is a heat generation element. that heat generation, how much amount of heat is generated per unit volume is given by QE. It's given by QE into LE divided by 211. The finally we are using this formula. Already you have used this formula for deriving for solving some problems that already you are used. Now we'll go back to the problem now. So first I'll start with the one problems on fins. Only there is slight change in because it is slightly, it involves more steps. That's why I start with fins. Or otherwise already we have I think there are 29 students. Please remaining 14 students, please enter your USN number. Please tell me, PPT is visible now? Yes or no? Please tell me, anyone can answer. Is the PPT is visible now?
Sir.
Yes?
Yes, sir.
Okay. So now already this type of problems are solved in heat transfer also. You have done same problem in your the ANSYS lab also. So it is we have wall, composite wall. So each it consists of three material. So each material is having K1, K2, K3. Because why you have to go for minimum you have to go for 3 elements, because K1, K2, K3 are differs. So as if you go according to the problem statement, we have composite wall consists of 3 materials as shown in figure. So once you say 3 material, so minimum you have to go for 3 element. You cannot go for only one finite element or 2 element. If it is the complete wall is made up of single material, then thermal conductivity is same. K1 is equal to K2, K2 is equal to K3. In such cases, if nothing is given, you can go for 2 element finite element model. But in this problem, they clearly mention it's a composite wall consists of 3 materials. Once you say 3 material, when you come to heat transfer problems, you are mainly concentrating on the property, thermal property. So one of the thermal property of the material is thermal conductivity K1, K2, and K3. So each material is having different thermal conductivity. Now, the normal you have the boundary condition. We have this is actual problem, but the problem statement they have given the diagram also. On the left hand side, they have given T infinity. So I am repeatedly telling that T infinity is not the T1 temperature. The T infinity is the surrounding temperature. Just I am giving the same heated rod or hot red dot rod, what you have seen done in forging lab. The temperature of the red dot rod may be 500 degrees Celsius. It will be around 700 degrees Celsius. That is, so if you model the red dot rod as a finite element, the temperature on the red dot rod is 500 degrees Celsius, 400 degrees Celsius, or some, and the temperature may be 300 degrees Celsius. The surrounding temperature may be 25 degrees Celsius or 30 degrees Celsius, because heat is from the rod, red dot rod, heat is transferred to the atmosphere by convection process. So because of the convection process, the surrounding temperature is given by T infinity. Even sometimes they don't give the T infinity like this. They'll put 2 arrows like this. They'll put 800 degrees Celsius that indicate that surrounding temperature. Don't consider T infinity is equal to T1, that's equal to 800. If you do that, if it is for a 16 mark problem, you will get 0 mark only. That's why, especially application of the boundary condition and knowing, putting the correct temperature, all those things are very important. On the right side wall, they have given T naught is equal to 20 degrees Celsius. It is not T infinity. This is nothing but the temperature T4. If you consider node 1, node 2, node 3, node 4, this is temperature T4. Then on the left side wall, there is a convective heat transfer. The right side, imagine you are heating the rod from the right side, the material, steel rod get heated, or this composite wall get heated, like your the furnace, it is heated from the inside. Imagine right side is inside wall, so your heat, it is heated, and temperature is from the inside wall to outside, comes through conduction. From conduction, the heat is transferred to the surrounding medium by convection, but it is in the opposite direction. Here there may be hot the gases, flue gases. The hot flue gases temperatures may be around 800 degrees Celsius. From hot flue gases, like you are studied about heat exchanger, inside the cylinders or inside the pipe, flue gases may flowing with very high temperature. The temperature is around 800 degrees Celsius. Imagine heat exchanger or heat pipes have two layer, first layer, second layer, third layer. The finally outside temperature is very less, because so it is having very, very low thermal conductivity. Even though inside the fluid is flowing at 800 degrees Celsius, but if you consider the outside wall of the fluid pipe, the temperature is only 20 degrees Celsius. This fluid is having the pipe is having three layer. The one layer is having different K1, another layer is having different layer K1, another layer is having different K1. That is a brief introduction about the problem. But you have to remember, so when you applying the boundary condition, you have to add H to the K matrix. That H you have to add for element 1 or at node 1, that we'll discuss later. The first part, this is your FE model that already we have discussed. You have to find out the thermal conductivity vector or thermal conductivity matrix. So we have two element, not three element, because it is taken from one of the examination. So element 1, element 2, element 3. I'm not describing each and every details. Whenever you are substituting the length you have to substitute in terms of meter. Don't substitute in terms of millimeter or centimeter. Finally, you are getting Q in terms of watt. To get Q in terms of watt, all dimensions should be in terms of meter, not in millimeter or not in centimeter. So now, so we know the formula for thermal conductivity. This K matrix or thermal conductivity matrix, it is given by AE K by L. So area normal to the heat transfer direction you are taking as a 1. Hence A is neglected. In most of the books they have neglected the A. That indicate that. So you are finding out the heat transfer per unit area, that is nothing but heat flux. Whenever you are saying heat flux, that is nothing but heat transfer per unit area is nothing but heat flux. So now you have to find out the thermal conductivity vector. It is almost like a stiffness matrix K1, K2, K3. In the similar way, you have to find out thermal conductivity matrix for the element 1, element 2, element 3, etc. But only difference is all dimension you have to keep in terms of meter. Then then we have three element, you have to find out the global thermal conductivity vector. It is nothing but so finding out the global stiffness matrix. No difference. It is almost similar to the bar. If you are familiar with the bar problems, then it is easy. Then we have finished. Then we have a global equilibrium equation. So where we have KQ is equal to F, but when you come to thermal equilibrium, we have KT is equal to Q. K is thermal conductivity matrix. It's a global thermal conductivity matrix. So T is temperature vector. So then I think strictly speaking, we have T1, T2, T3, and we have T4 also. It is missed. T4 is also there. Here it is missed. There is some mistake here. Then R1, R2, R3, and R4. So there are 4. It is a 4 by 4 matrix. T4 is missed here. That's all. Nothing else. T4 is missed here, and R4 is also missed here. Please note down. So because we have, you have to go back and check the elements here. T1, T2, T3, T4. In a similar way, we have T1, T2, T3, T4. It is given here. Then R vector is 0 because no heat generation rate here. So hence R vector is 0. Otherwise, you can write the formula. So where R infinity is equal to, we have the formula, just we have derived the formula, R infinity is equal to Q LE divided by 2 1 1. So as Q is equal to 0, so no heat generation is taking place within the element. Here you can see. So no heat generation is taking place. So imagine in element 1 also no heat generation, element 2 also no heat generation, element 3 also no heat generation. Hence, the heat generation vector for element 1 is 0, 0, 0. Here element 2 also it is 0, 0. Element 3 also it is 0, 0. No heat is generated within the element, or in simple way with respect to your bar element, if there is no external loading, then your force vector becomes 0, 0, 0. There may be thermal load, but there is no external loading. Then in such case, you are writing 0, 0, 0. Then in the similar way, your R value is 0, 0, 0, 0, 0. Then you have to add one more factor. You have to remember, this is very important when it comes to heat transfer. There is a convective heat transfer at node 1. There is a convective heat transfer between node 1 and surrounding. Hence, you have to modify the thermal conductivity matrix. At the same time, you have to modify the force vector also, thermal force vector. So most of the time, the students will do the mistake here. They'll find out the K1, K2, K3 correctly. They'll find out the global matrices. But so there is a convective heat transfer taking place at node 1. Hence, for the diagonal element 1, you have to add convective heat transfer coefficient. So in your test also, if second test is online test, then you may expect such type of questions. So suppose, so convective heat transfer takes place between at node 1 and the surrounding medium. So H is added to first diagonal element, second diagonal element, third diagonal element, or fourth diagonal element, or H is added to K11, K22, K3. This term is K11. This is the first diagonal element. So 4 correspond to K22, K33 is correspond to 8, K44 is correspond to 5. K44 is the thermal conductivity value at fourth row and fourth column. In mathematics, it is referred as K44. In our problem, the convective heat transfer takes place at node 1. Hence, you have to add H to K11 or first diagonal element. In the similar way, so in the force vector also, you have to add H into T infinity. That modification, it is a global equilibrium equation. You are not applying the boundary condition. There is a convective heat transfer takes place at node 1. Hence, you are adding H at diagonal element. In the similar way, in the first row of force vector, you have to add H plus H into T infinity. That this step is very, very important. The remaining previous steps is exactly similar to the bar problem. Here, only difference. Now, I think I have shown this. I think there may be mistakes here. So since no heat generation, already you have written 0, 0, 0 here. R1, 0, 0, 0, 0. So how you are getting 0, 0 is, so RQ already you have derived QE, LE divided by 2, 1, 1. But L we have, 2 we have, that is a constant, but Q is equal to 0. There is no heat generation within the element 1. There is no heat generation within the element 2. There is no heat generation within the element 3. Hence, so R1 becomes 0, 0 if DOFs are 1 and 2. R2 becomes 0, 0 if DOF is 2, 3. And R3 is DOF again 0, 0. We can write 3, 4. The examination, if you don't have the time, you can straight away you can write RQ of 1 is equal to RQ of 2, that's equal to RQ of 3, that's equal to 0, 0. Straight away you can write. But if you write in details, you have advantage. If final answer is even by mistake calculation, if you done mistake, for that at least steps will get majority of the mark. So now, so after, because we are adding head to the first diagonal element, original value is 6.66.66 plus plus you have H value is 25. H value is 25. The finally we get around after taking the multiplication factor of 666 etc. Because you have to do it separately because already we have the multiplication factor. I think multiplication factor is mixed here. Once again, you also do the mistake. Don't do the mistake. Here also you have the multiplication factor of the 66.66 here. The outside multiplication factor is 66.66. So here also you have the multiplication factor 66.66. Here also you have the multiplication factor 66.66. So hence, so we have 66.66 plus 25. If you come back here, it is 1. Here you have the multiplication factor 66.66. So this correct value is 66.66 plus we have 25. So we get 91.66. We are taking the multiplication factor 66.66 outside. Hence it is multiplied by 1.33, or we have 91.66. So divided by the multiplication factor 66.66. Hence we are getting 1.375. Because you are keeping the multiplication factor outside, that's why you have to do it separately. K11 dash or revised or updated value of the K11 is given by 1.375. So originally in even finite element package, the original value is saved in the system. Then later stage there is an updation of this, the thermal conductivity values. That's the one part. Then so we have on the right hand side, we have R1 plus H infinity, H into T infinity. So R1 is 0. So H into T infinity is, the H value is 25 Newton per meter. Some value is given, it's in terms of meter only. So H value is 25 and T infinity is 800. Finally, we get 20,000. Here we get 20,000. That's the first part. So we are not applied boundary condition, just we have added H to diagonal element 1. Also, you are added H into T infinity to the force vector, the first row of the force vector, because we are applied there is a convective heat transfer. But now you are not applied the boundary condition. We have given one boundary condition is there here. So at node 4, the specified temperature boundary condition. At node 4, the temperature is 20 degrees Celsius. It is not zero boundary condition. It is a non-zero boundary condition. It is also referred as non-zero, non-homogeneous boundary condition. In the case of non-homogeneous boundary condition, the value of temperature is not equal to 0, or value of the displacement or value of the rotation is not equal to 0. In such cases, we cannot eliminate the fourth row and fourth column. You have to eliminate fourth row and fourth column, that I'll agree. So once you eliminate fourth row and fourth column, you have to change the force vector also. So once you eliminate this, so then you have to change the force vector. We have when you how to change the force vector, shortcut method is, so we have you are eliminating this row. So that means this is K31, K14. You are eliminating this row. So this K14 goes to here, K14 into, you are applying the boundary condition at node 4, that is T4. The second term is K24 into T4, and third term is this is, so this is K34 into T4. That detailed already it is solved. It is already circulated. This how to apply non-zero boundary condition for thermal problems, or even for this regular structural analysis problem. I have spent almost 2 hours or 3 hours how to apply non-zero boundary condition. In simple way, you have to remember, I have one more slide also in general term. In simple way, you are eliminating third row, the fourth row and fourth column. Just concentrate on the fourth row. When you are eliminating this fourth row, so this term goes to right side. This is correspond to K14. K14 into T1, you are going for the multiplication. It's a simple matrix multiplication. 1.375 into T1 minus 1 into T2, 0 into T3, the 0 into T4, the T4 value is known, that is a constant value that you are taking to the right side. That means T14, K14 into 20, and second term is, here you will get one more minus K24 into T4. T4 is common everywhere, multiplication. Then third term is K34 into T4. This step is also very important. So that is separate notes also, I think already I given. Just go through it. So especially when you handling boundary condition for non-zero boundary condition, most of the heat transfer comes under the non-zero boundary condition. I have prepared the detailed notes. I think I have not circulated. Once again, if you want, I will circulate for non-zero boundary condition in terms of matrix it is given. So now after eliminating you are eliminating fourth row and fourth column. Only difference is here temperature is not equal to 0. If temperature is equal to 0, just we can eliminate fourth row as well as fourth column directly. So now by using your calculator, I think if you are using 77 series Excel, you have to go for mode 1, 2, 3. I think you'll get one equation mode. The equation mode, if you can get the value of T1, T2, T3. I think after elimination, you'll get this value. So from this equation, we can get the unknown parameter T1, T2, T3 are the unknown parameter. I think another 10 students are not entered your USN number. Please spend few seconds for entering your USN number in the chat box. That is records you are present for the class. I hope this is the PPT is visible. I'm going. I hope it is PPT is visible. Yes or no? Yes or no? PPT? Someone can answer. Yes or no?
Yes, sir.
Okay. Then we'll go for one more problems on fins. So now, there are two types of engines. One is air-cooled engines, and all those things you studied in your thermodynamics 1, thermodynamics 2, or even heat transfer also you have studied. Whether fins are started in your heat transfer fin chapter. There is some derivations, but don't worry about that. There is only one formula as per your FEM is considered. You have to understand the basic concept of fin. So you are familiar with two types of engine cooling. So one is air cooling and one more is the water cooled. So most of the four-wheelers, it is a water cooled engines. There is a heat exchanger or normally referred as a radiator. But in come to two-wheeler, to make the vehicle compact, if you go for radiators or heat, whatever the amount of heat generated inside the engine, finally it goes to the surrounding medium. Otherwise, if the temperature of the engine increases, when temperature of the engine increases, because of the piston is having lightweight material, so piston it may expand. When piston expands, so piston may struck inside the cylinder. That's why whatever the amount of heat, some amount of heat is used to do the work done. That is, so during the combustion process, heat is generated due to burning of the fuel, the air fuel mixture. So then some amount of heat is converted into mechanical work by pushing the piston in the forward direction, and it will generate the power. Finally, it can drive the vehicle or whatever it may be. Some amount of heat is still there in the engine itself. That amount of heat you have to extract from the engines. That means finally it goes to the surrounding medium. Otherwise, engine temperature increases and it may not perform well the most of the time. So your piston gets stuck inside the engine, inside the cylinder because of, so as temperature increases, there's a more expansion. Because of more expansion, so the clearance between piston and cylinder is very, very small. So that's why there are two types of cooling. One is air cooling and one more is water cooling of the engines. So now if you go for the water cooling, then your two-wheeler become more, weight of the two-wheeler become more and more. So that's why especially for the two-wheeler, no, they'll not go for any water cooling. So they're going for the air cooling. So in general, concept of your heat transfer is, so whether it is a convective heat transfer or conduction heat transfer. So we have heat transfer rate, or even if you come to the conduction equation, we have Q is equal to K into delta T into A divided by L. That means your heat transfer rate will increases when the surface area increases. Even for the conduction also, if the area normal to the conduction, if heat is flowing along the x direction, if you increase the area normal to the x direction, then heat transfer rate will be increases because your heat transfer rate directly proportional to the area in the case of conduction. When you come to the conduction equations, we have Ka as per your heat transfer is considered, heat transfer subject is considered Ka delta T by L. As area increases, the conduction heat transfer increases. When you come to the convection heat transfer, we have the formula for convective heat transfer. So H into A into T minus T infinity, or T surface T naught minus T infinity, or T surface minus T infinity. Suppose we have the hot rod, the temperature of the surface is Ts, the surrounding temperature is T infinity. If there is a more difference in temperature, because of the difference in temperature, the more amount of heat is transferred from the solid material to the surrounding medium. So that means again, when you come to the convection, we have convection heat transfer is equal to H into A into T minus T infinity. The T infinity refer to the surrounding medium or atmospheric temperature. Then compared to atmospheric temperature, the engine temperature is more. Because of the difference in temperature, heat is moving from the engine to the surrounding medium. So then there is a one more factor. So we cannot change the atmospheric temperature. If you reduce the atmospheric temperature, there is a more amount we can temperature difference is more, or delta T is more, then there will be more heat transfer. But it is not in our hand. We cannot reduce the atmospheric temperature. We cannot increase the temperature of the engine itself. It will not serve our purpose. Next, only one option is you have to increase the surface area. So we cannot make the bigger engine. So instead of making the bigger engine, we can have the small fins. Imagine this is the engine surface. I think if you closely observe the engine, you can small projection you can see in the engine. Just be adjacent to the engine or outer surface of the engine, we can say the small fins or the projection. So those projections are referred as fins. So because of these projection, the surface area will be increases. As surface area increases, the more amount of heat is transferred. In simple example I can give is, imagine you have a cup of coffee. Imagine it is very hot. If you keep it in the cup of coffee, you have to wait for 5 to 10 minutes. You have to wait for 5 minutes to come to temperatures to comes down. Instead of keeping the cup of coffee in the cup itself, put it in the regular meals plate. So within 1 minute, the temperature comes down, because where the surface area is increased. As surface area increases, there is a more convective heat transfer. Here also, even though engine may be having high-end technology, also we may say engine high technology is involved. Here also same simple concept is used. So if you increase the surface area, there is a more amount of heat transfer by convection. Same concept is used to increase the surface area. They have added, imagine this is the wall of the engine, or outer surface of the engine, this vertical wall. Here we are putting the fins. This is rectangular fin. Most of the time it is rectangle, but this it is not like this corner. There is a curved here to get better look and safety purpose. They have curved. For our analysis purpose, we are going for the rectangular fin. Imagine this is a fin. So in finite element analysis, this fin you can divide into three elements: element 1, element 2, element 3. So how much amount of heat transferred in the element 1? Imagine we have the fin, this plate. This is fin is nothing but a small plate. It is welded to the wall of the engine. So we have divided the complete fin into three element. Amount of heat transferred to the surrounding medium by element 1 is given by QH1. The amount of heat transferred to the surrounding medium is given by T2. And similarly, amount of heat transferred to the surrounding medium by the fin 3, the element 3 is given by H3. Then the total heat loss or total amount of heat transferred from the fin to the surrounding medium is given by QH is equal to I is equal to 1 to 3. That means the total heat loss is given by this formula. Now I come to the directly problem, that is normal standard question, because most of the time we may get 2 element problem, but in I am doing 3 element problems. Even wall also I have done 3 element problem in the composite wall, so that in the examination if 3 element wall means, so we may require more time, but most of the time we may expect 2 element wall. So now you are considering 3 element fin. So if you come to the
क्लास भी नहीं है, इसलिए ये तो तय है कि वो मर चुका, ये नौबत नहीं आती।
yes. So now a metallic fin with thermal conductivity K is given and thickness is anyhow it is given in the centimeter, but you have to convert into meter. That you have to remember. And temperature and extend from a plain wall whose temperature is 235. Imagine engine surface temperature is a plain wall. The engine surface temperature is 235 degrees Celsius. Determine temperature distribution amount of heat transfer from the fin to the air at 20 degrees Celsius. So surrounding temperature is 20 degrees Celsius. This is air temperature. So from the fin, it is a solid surface. From solid surface to the surrounding area, a medium. The surrounding medium is nothing but a fluid. So that heat transfer takes place by convection. And convection, the heat transfer coefficient is also given. H is given. Take the width of the fin to be 1 meter. That most of the time they'll give. Sometimes they'll give the statement width of the fin is to be 1 meter. But if it's not given, you have to assume width of the fin is equal to 1 meter. Now, if we come to this is the finite element model. You are going for 3 element. This is element 1, this is element 2, and element 3. The total length of the fin is 10 centimeter. Then you will get element length of the element 1, element 2. 10 divided by 3 gives the length of each element. So in general, so fin is mounted to the wall of the engine, relative wall of the engine. The wall temperature or temperature T1 with respect to this diagram, the temperature T1 is given by 235 degrees Celsius. Our aim is to find out, so what is the temperature at node 2, what is the temperature at node 3, and what is the temperature at node 4. And in one more boundary condition is, so if the thickness of the fin is very, very small, or if you see the cross section, imagine, so top surface is having huge surface, bottom surface also having huge surface. And if you consider this surface, the end surface, this cross section area is very, very small compared to top surface as well as bottom surface. When cross section area is very, very small, then heat transfer is also very, very small. In such cases, we are assuming that there is no heat transfer. That means tip of the fin is insulated. So that's why you are writing other end. The tip of the other end of the fin, the cross section is very, very small. The heat transfer rate is very, very small. Don't think that it is insulated by putting rubber, etc. It is not insulated. Area is very, very small compared to the surface heat transfer. The tip heat transfer rate is very, very less. Hence, you are putting Q is equal to 0. Then, as usual, first part is you have to find out the thermal conductivity for the element 1, thermal conductivity for the element 2, thermal and global thermal conductivity vector. That's the first part. Then element convective matrix. So this formula is different for the fin. Only this formula you have to remember and you come to the problem sum fins. So because there is a convective heat transfer from the fin surface to the surrounding medium. It is a fin is nothing but a projected area. So that convective matrix, convective matrix, that convection matrix you have to remember. It is almost similar to your thermal conductivity matrix. When you come to fin, we have thermal conductivity matrix. From that you are getting global K value. This is nothing but a global K. Already we have the global K. In the similar way, extra matrix you have to remember is the convection matrix. The convection matrix is given by H of T is equal to H into LE divided by 3T. The T refer to thickness of the fin. H is given convective heat transfer coefficient. So LE is length of the fin, because total length is 10 centimeter. 10 divided by 3 means you get 3.33. It is in centimeter. That you are converted into meter. That's why you are multiplied 10 to the power minus 2. So only one difference from the previous problem and this problem is we are adding one more additional matrix. That is nothing but convection matrix. This formula you have to remember, H into LE divided by 3T 2112. That is slightly different. So you are getting convective heat because you are divided the fin into 3 elements. Some amount of heat is transferred from on the solid material itself. For that reason, you are considering thermal conductivity matrix. And some amount of heat is lost. Some amount of heat is moving along this direction because of conduction. That's why you have to consider conduction matrix. And some amount of heat is lost on the top surface as well as bottom surface. That is by convection. Hence, you are considering convective heat transfer. You have to find out convective heat transfer for element 1, convective heat transfer for element 2 matrix, element 2, In the similar way, convective heat transfer matrix for element 3. From that, you have to get the global matrix. Global matrix is given by H of T. Now, this is a global matrix. Then, similarly, there is a element heat load vector or heat force vector. For fin, this formula is different. In the fin, there are two formulas you have to remember. One is convective heat transfer coefficient, convective heat transfer matrix, and one more is the heat force vector. R infinity is given by H into T infinity divided by LE divided by T. That is the R infinity matrix. So don't refer any books. So I think if you refer books or some local books also, you have some confusion. They are not used in different method. But I have done this formula according to derivation according to the Chandrapatla. That is the international edition book. That's a good book. I have followed that book only. I have used that notation also. Some book they adopted different method also. Sometimes you may get different answer also. Especially for the complete heat transfer for derivation as well as problems, refer my notes. Now this matrix you have to remember. R infinity matrix is the one matrix you have to remember for the fin, and one more is the 2H matrix. So I'm going to derive those equation also. First practice for conduction equation, then I'll take some other day I'll derive those two matrices, another two matrices. But now for solving the problem, if you remember the final matrix, that's sufficient, because tomorrow I'm going to start with the module 5. Now this is R infinity. So you have to find out R infinity for the first matrix. There is a where in the previous case it's RQ. This here you are referring as a R infinity. There is a difference between RQ. RQ is equal to QLE divided by 2. That is RQ matrix. But when you come to the fin, there is a totally different matrix that is referred by R infinity matrix, or it is also referred as heat force vector. It is nothing but how much amount of heat is transferred to the surrounding medium from the fin surface. So similarly, you have to get R1, R2, R3. Then afterwards, you have to find out the global. It is almost like a force vector. We have F1 for the element 1. We have the F matrix. You have done some problems on UDL. First, you have to find out the UDL for the element 1. Then you have to find out the UDL for the element 2. Then you have to combine those two. So that is given by the final R vector. Now, when you then total K value, it is not thermal conductivity. On the left hand side, we have a matrix that is by K. K is equal to KT plus H. So KT referred to the global thermal conductivity matrix. H is referred to the convective heat transfer matrix. That already H value we have. This is the HT. We have H1, H2, H3. From H1, H2, H3, you are getting HT matrix. Already we have K1, K2, K3 we have. From K1, K2, K3 we have KT matrix. There is one more difference in step. So here on the left hand side, we have K matrix is KT plus H. It is just summing of this, element to element summing. It is not you are adding 10800 plus 198. So it is just summing. It is not like taking some element from here and there, etc. It is just matrix summation. So you are writing K is equal to KT plus H. It is just matrix summation. You know, no DOF is involved. We have first term is 10800 plus 198. If you come to the fourth column 0, no other term, like that. If you come to the last element 10800 last element in the H matrix is 198. It is just simple matrix addition. Add those two matrices, then so you are applying boundary condition at node 1. Temperature is given at node 1. So here T1 is equal to T0. You are eliminating first row as well as first column. When you eliminate in the first row and first column, after eliminating, so you have to take this term 10701. It is nothing but K21 into T1 T0, K31 into T0, K31 into T0. This part you should be very careful. I think today I'll circulate that notes, that especially boundary condition, non-zero boundary condition, by using penalty approach as well as elimination approach. Go through it. Everything is given. In simple, you are eliminating first row and first column. So anyhow, first row is gone and first column is gone. Then you have to subtract the force vector, the heat force vector, this 10701 into T0. So 10701. So here left side, here you are eliminating the term. 10701 is the left element. that is we are eliminated. Eliminated is in the sense you are moving to the right side. So 10701 into T naught. Similarly, 10701 into T naught, 0 into T naught. All term will comes to the right side. This step you should be very, very careful. Complete derivation is there for elimination approach for non-zero boundary condition. You refer once again. I already spent around 3 hours for that. So now finally you are getting, you have to get T1, T2, T3, etc. So from that, from the calculator, we can get the value of T1, T2, T3. I am not mentioned here, but when you come to element, just 2 minutes, I'll finish it off. So the temperature at node 1 is known and temperature at node 2 is known. So now we require average temperature of the element 1. T1 plus T2 divided by 2 refer to average temperature. Similarly, for the element 2, T2 plus T3 divided by 2, that is the average temperature. In the similar way, for the element 3, the average temperature is T3 plus T4 divided by 2, that is the average temperature. By using that average temperature, that you can see here, the heat loss is equal to H into, we have the standard convection heat transfer matrix. So heat transfer H into T average or T surface minus T infinity due into AS. So AS you are taking as a 1, I think AS you are taking as, I think AS you have to find out. AS you are getting 1.006. So now you have to find out the average element temperature of element 1. This is the average temperature of the element 2. This is average temperature of the element 3. After getting average temperature of the element 1, you have to find out what is the heat loss from the element 1, what is the heat loss from the element 2, what is the heat loss from the element 3, and total heat loss by the fin is given by this equation. So surface area is, I think somewhere it is mixed, I think. So surface area is, we have a surface area is, the width of the fin is 1 meter, but so area of the fin is given by this length is somewhere here. Length of the element is 0.333 into 10 to the power of minus 2, 3. I think somewhere I mentioned area. Otherwise, it is missed, I tell you. The thickness is 0.1 meter. So this area they have considered. So finally, you are getting the area 0.066. Otherwise, I'll add one more slide here for the tomorrow class. I will explain how you are getting the area. You may have doubt. It is missed here, notes. So I will show how you are getting 0.666, etc. So I will continue tomorrow. Only this part I will explain, or I will take around another 5 minutes. Tomorrow I will spend around another 5 minutes for explaining the problems on heat transfer through the fin, along with this area, how to get the value of area. Then I'll start with the dynamic analysis. First, I'll start with the problem so that you'll understand better. Then we'll go for the derivations. Dynamic analysis is nothing but your continuation of your vibration chapter, what you studied in DOM. Last 2 chapters you have studied. Okay, I think thanks. We'll meet tomorrow. You can leave the session.
Okay, sir.
Okay, thanks. So you can leave the session and you can join for the next class. Complete notes is given to you. So practice those derivations as well as problems. If you have any difficulties today itself, you practice. If you have any difficulty, tomorrow you can get clarification from me. Don't keep your doubt for a long period of time. If you have the doubt, what I have done today, tomorrow itself you have to take the clarification. If some other day also you can take the clarification, but tomorrow is the best day. Our portion I covered. If you ask some doubt, first 5 minutes or last 5 minutes, we can discuss.